So this is 3.2 gases. All right, there are three different properties of gas that we're going to be talking about. We've already really kind of identified one, and that's volume. What's volume? Go ahead. All right, so the space an object takes up. Now, when we talked about gases, we identified just a few minutes ago that they expand to fill their container, meaning that if their container is large, they take up a whole bunch of space. If their container is small, they take up very little space. So I want you guys to think about this for a second. Treat yourselves as gas particles. Your container is the classroom. So we've got plenty of space. You don't really have to do a whole lot to make sure you've got your space. However, if we took you all and made you all sit at this front table, what's one of the first things you would probably notice? It's very small. Say again. It'd be hot. So the first thing we're going to talk about here then is temperature. Temperature, which you guys yesterday identified as the average measure of kinetic energy. A measure of kinetic energy. Okay. For volume, what are some things that I could measure that in? What have you already measured volume in this year? Milliliters. Or liters is good. What else have we measured volume in? Yeah. Not quite. Now you're talking densities. Centimeters cubed. Okay? Milliliters or centimeters cubed, which are actually 1 milliliter is 1 centimeter cubed. They're really the same thing. 1 milliliter is 1 centimeter cubed. Okay? For temperature, we're typically going to measure this in Kelvin. Kind of similar to degrees Fahrenheit or degrees Celsius, but Kelvin is the SI unit for temperature. All right, so we've moved you all to the front table. You've noticed it's got hotter. What else would you notice? Yeah. Be a lot more crowded. All right. Anything else or another way to put that? A lot closer together. Okay. So with being a lot closer together, a lot more crowded, that's analogous to what we would call pressure. All right. And if we think about putting a fifth person at this table, that'd be pretty easy, right? How about a sixth, seventh, and eighth person? It started to get crowded, but not too bad. 9, 10, 11, 12. Now we're starting to get unreasonable at one table. And as you add each additional person, it gets harder and harder for you to actually have that space. Well, that's kind of what pressure is talking about. Pressure is an amount of force per area, and amount of force per area. And basically, it's the resistance to adding more things to a single location. Resists adding more pieces to a location. Typically, we're going to measure pressure measured in, we can talk pounds per square inch, PSI. We could talk atmospheres. You are currently under 1 atmosphere of pressure. We could talk millimeters of mercury, mmHg. Okay? All of these different things are different ways of measuring pressure. We could also talk pascals or kPa, kilopascals, which you'll see on a worksheet later today. Questions about what volume, temperature, or pressure are? All right. Then we're going to talk the relationships between these, which are called the gas laws. First gas law that we're going to look at relates pressure and volume, and that's Boyle's law. Boyle's law indicates that as the volume of a gas decreases, the pressure increases. As the volume of a gas decreases, the pressure increases. Can anybody give me an example of something that you could decrease its volume and it'd push back harder, or it'd have higher pressure? Typically you don't squeeze an oxygen tank. That sounds like it could be very dangerous. Yeah? Okay, a balloon. So probably a little safer to squeeze than an oxygen tank, but same idea. As you squeeze a balloon in, what's it liable to do? Pop. Because the pressure inside has increased and you have more force pushing out on each individual spot. So this would be like squeezing a balloon. Another example. What would be another example of Boyle's law? Yeah. With lungs, yeah, you could count your lungs because as you physically decrease the volume of your lungs, the pressure has to change. Well, I don't know. You're also changing the number of particles in there because it's not a closed system. So I don't think lungs is a great example. Yeah, Maddie, what were you going to say? Yeah, go ahead. mmHg, millimeters of mercury. All right, so another example of Boyle's law, we could have something here like bubble wrap. Okay, or if you drive over a rock in your car, your tire's volume becomes compressed and the pressure goes up. Or if you overload your vehicle with a whole bunch of stuff, you see the tires start to look flat and the volume has decreased as the pressure has gone up. So overloaded vehicle tires. You had one you wanted to add? I'm not sure I know what you're talking about. That's not quite the same because that has more to do with the flow of the particles, and we wouldn't be keeping them constant in that case. Um, Basically, anything where if you squeeze it, it feels like it's going to burst, we're probably talking about Boyle's law here. Next one up is Charles' law. Charles' law is a relationship between volume and temperature and indicates that as the volume of something decreases, or sorry, as the temperature of an object decreases, the volume will decrease as well. As the temperature of a gas decreases, the volume will as well. Anybody have an example here? Go ahead, Caleb. A basketball when what? All right, sounds good. Actually, any sports ball. So if you leave a sport ball outside over the winter, you'll notice that it definitely shrivels up. Others. Other examples of Charles' law, where temperature changes the volume. Say again? I don't think so because I don't think we're talking about a gas there. Hassan? So it's a similar idea and it's based on the same, but I'm not going to write that one down because that's not talking about a gas, but it is a very similar idea. Okay, I can also talk here about like carrying a balloon outside in the winter. Anybody a driver yet? Anybody have their driver's license? Anybody in driver's ed right now? Okay, so I've got one that's in driver's ed right now. So one of the things that you guys will notice as we go into winter, and you'll notice this a lot more once you actually become drivers, is that as it gets colder, your tire pressure goes down. So this is largely due to the change in volume that we see, but we can relate Charles' law to your tires deflating here. So I'm going to keep these two, and then we're going to go on to our last one here, Gay-Lussac's law, which is actually probably a better representation of the tires and temperature, because this tells us that as the temperature decreases, so does pressure. Decreases, so does pressure, which would be like car tires in the winter. Okay. Anybody think of another example there? Okay, well, we'll settle with those. So looking at these three laws, I want to know which of these laws has a direct relationship between the variables. Charles' law. As one decreases, the other also decreases. So this is a direct relationship. Do any of the others have a direct relation? How about an inverse relationship? Do any of them have an inverse relationship? Maddie? Right. Boyle's is going to be an inverse relationship. And what does that make Gay-Lussac's law? Say again? As one goes up, the other goes down. But Gay-Lussac says as one goes down, so does the other. So direct. All right. Last thing we're going to have on these is for Boyle's law and Charles' law, we actually get an equation for these, where Boyle's law is pressure 1 times volume 1 equals pressure 2 times volume 2. Meaning the pressure and volume of an object before something's done to it is equal to the pressure and volume of something after something's done to it. Same with Charles' law, V1 over T1 equals V2 over T2. The volume and temperature before something's done to an object are equal to the volume and temperature after something's been done to that object. So last chapter, the equation you guys got was the density one, D equals M over V. This chapter, we get Boyle's law, P1 D1 equals P2 V2, and Charles' law, V1 over T1 equals V2 over T2. You guys are going to have to be able to use Boyle's law, and that's what we're going to spend most of today working on. If you are interested in extra credit, you're going to need to be able to use Charles' law. So everyone's going to need to be able to use Boyle's. People interested in extra credit are going to need to be able to use Charles. Good with that idea? Okay. Let's go ahead and take a look at an example here then. So who am I going to pick on? I'm going to pick on Logan. That's a good question. Squeezes a 1 liter balloon that is filled if you want to have the example in your notes, yes, to 25 psi. If after he squeezes the balloon, it now has a volume of half a liter, if after he squeezes the balloon, it now has a volume of 0.5 liters. What is its new pressure? On both sides. And what's my answer going to be? Remember, it's got to go up. Say again? 50. So we have 50 psi as our answer. Questions about how we solved that one? All right. So before we start practicing on these, one last thing that I want to point out about the gas laws. What property of a gas does Boyle's law not talk about? What property of a gas does Boyle's law not talk about? Yeah. That's state of matter. I'm asking gas property. Temperature. Boyle's law doesn't talk about temperature. That means temperature is always constant for Boyle's law. What property of gas does Charles' law not talk about? What gas property does Charles' law not talk about? Pressure. That means pressure is always constant for Charles' law. What gas property does Gay-Lussac's law not talk about? Volume. That means volume is always constant for Gay-Lussac's law. All right? So if it's not mentioned in the law, then that means it doesn't change for that law. Good? All right.